Hey class, welcome back. And now we're going to talk about the pre-lab for pre-lab number 2. So again, you should have downloaded the lab. You should have attempted all of these questions on your own. And in this lab, there's a lot of derivations. So you need to have tried to work through from our basic kinematic equations to an answer. If you have nothing, if it's just blank, you need to pause and really think about it. Treat it as if each of these are like a homework question, but you're going to be solving them in variable form rather than dealing with them with actual numbers. So please give it a good try, fill out the My Attempt column, and then you can watch this video if you haven't done so already. All right, so let's jump in. All right, so you should have something that looks like this. Again, your pre-lab with all of your answers on one side and a blank column on the other. So for this one, I'm going to kind of tackle most of these kind of together at one time, or at least the first 3 of them. So what you're doing in this lab is you're going to have some sort of a ramp as shown here in blue, and that ramp is going to be set on like a table or a countertop or something, which is the black table here. And you're going to have a ball like a marble or something that's going to roll down the ramp. And just before the end of the table, you have a little bit of a flat region so that then whatever the speed of the ball is as it comes off the ramp will be the horizontal speed as it comes off the table. So the idea behind this is this velocity here, which we might call V2 of the ball at an angle down the ramp, will be equal to V3 in magnitude, but V3 is going to be directly horizontal, which is really important for working through this derivation. So as we're going to do this here, I want you to think about taking this problem and sort of breaking it into 2 pieces, right? So if we kind of cut it right down the middle here, you're going to have part 1, which is analyzing from points 1 to 2 in my drawing, which is the top of the ramp when it's stationary to the bottom, and then analyzing a separate time here from point 3 to point 4. So keep that in mind. Let's start by thinking about analyzing from point 1 to point 2, which is when it's on the ramp. And like any other time, let's think about breaking it down in terms of our kinematic variables. So point 1, V1 would be our V initial. In this case, though, before I start to break down V initial, V final, X, Y, and so on, we need to think about axes. So what I'm going to do in this problem is I'm going to define my x-axis as parallel to the ramp, okay, in the downward direction, and my y-axis, excuse me, as perpendicular to the ramp. So all of my motion, everything's going to just be in the x direction. Let's even come down here and just kind of make a note to ourselves that we're going to analyze x direction only. So what that means then is our V1 is our V1 in the x direction, and that's the initial velocity it starts with, which will be 0 meters per second because we're starting from rest. And based on my axes, our x initial, our starting position, or really maybe I should say x at point 1, if I use subscripts that correspond to my numbers up there, that's going to be 0 meters. And then if we look here, our V final, which is V2 in the x, we don't know. And in fact, that's what question 1 is asking us to figure out, is what is that speed it has at the bottom of the ramp. And my x2, my position at the bottom of the ramp, I'm going to just go ahead and call D. So that's something we're going to measure, but that's the distance D from where it starts to the bottom of the ramp, okay? And that's something that you might vary during the lab. And then the time T, we don't know how long it's going to take to go down the ramp. And as we learned last week, measuring real quick times isn't always the most accurate. So we're not sure about that. But the acceleration is kind of a fun one. The acceleration in this x direction is actually going to just be the acceleration due to gravity multiplied by the sine of the angle theta, where angle theta is the angle of the ramp. And some of you might be like, whoa, wait a second, where does that come from? And that's an excellent question. It's a little bit tricky. But if I kind of come over here and if I just kind of pull the ball, if I draw maybe off to the side, here's my ramp. And if I put the ball on the ramp here, we know that gravity is pulling on it in a straight down direction. However, as we're going to be learning about, or have already learned about really with vectors, if I think about, again, my axes like this, calling this x and this y, we can think about some of this gravity is just going to be pushing down into the ramp. So like a piece of this gravity what I might call GY is just straight down into the ramp. And then part of this gravity, which I would call GX, is down the ramp. And so if I wanted to, I could actually take my G and turn it into a little right triangle. GY being the component of it that's straight down into the ramp. And then my GX in this direction, which is the component down the ramp. And this is a right angle because X and Y are always perpendicular to one another. And the cool thing is that you can prove this with geometry, as you'll see in the lecture videos. But again, if this ramp has an angle theta, then since we rotated our axes by theta degrees, we would find that this angle here, shown here, is also theta. And so therefore, since we know sine of the angle theta is equal to the opposite over the hypotenuse, then GX is just going to be equal to G times the sine of the angle theta. So that's where that comes from. So figuring this out, that the acceleration down the ramp equals G sine theta, is often the trickiest part of this question for a lot of people. But that's part of why watching this video is very helpful. So now what we can do is we can use one of our kinematic equations. We're trying to find the final velocity. We know the distance, but we do not know the time. And so what I would recommend is using our one kinematic equation that does not include time, which tells us v final squared, or in this case, v2x squared, is going to be equal to v1x squared plus 2ax times x minus x final, in this case, x2 minus x1, or the displacement. And since v1 initial is 0, what that means is v2x that we're trying to find is the square root of 2ax, which is g sine theta, times the displacement, which is just d. And so our equation could be simply v equals square root of 2g sine theta times d. Or there's actually one more pro tip I can show you just for fun. We go back up here to our triangle. Let's just draw it again because that picture is getting crowded. We draw our ramp. One other thing that you can do is if we call d the distance down the ramp, and if we call the height of the ramp h, and if we know this angle is theta, in the same way that gx was g sine theta, h is just equal to d sine theta. So you could actually come back down here, rewrite our equation here, and just say that v2x would actually just be the square root of 2g times d sine theta, or 2gh. So the speed at the bottom of the ramp is the same as if you just dropped the ball straight down and it fell a distance h, which is a kind of cool thing to show in this scenario. So anyway, either of these two is acceptable for your answer to pre-lab question number 1. Ooh, but that was a lot. That's just question number 1. Well, 2 and 3 will go a little bit faster for us. Now, what we're going to be doing for question 2 is we're asked, what is the time it takes for a ball dropped from a given height? So really what we're being asked is to think about this second part here. When the ball is going off the table at point 3, how long is it going to take for it to reach the ground? The question just says if it's dropped straight, but as we are learning, right, whether it's thrown horizontal or dropped straight, it's the exact same either way. So we're now going to analyze from points 3 to point 4. So I'm going to come over here off to the side. And we want to kind of go through the same process that we're doing. I'm going to do blue this time so that we can distinguish it from what we've already done. But if we think about V3, now we're going to have to break it into X and Y. Right now, we're just concerned with Y. So V3Y is going to be 0 since it's going straight horizontally off the table. Y3, the position there, is going to be the height of the table. So maybe we'll call this H3 or something, where H3 is the height of our table. I just am giving it the subscript 3 so we don't confuse it with the height of our ramp that I was just discussing. So really what that means is this height over here, we might want to call like H1 or something. Okay, so we got Y3 equals H3. Our time that it's in the air is what we're trying to figure out. Our acceleration in the Y direction we know is just negative G, and we know that V4Y is, well, unknown. And then we know Y4 is just going to be 0 because it's hitting the ground. So again, what we're doing is we're defining axes that looks something like this, where a 0 point in the y direction is at the ground. And our initial x position will be 0, as we'll see in a minute. So to find the time then, in similar fashion to what we did last week, we can use our second kinematic equation of motion, second kinematic equation of motion, which tells us that y final, which is y4, equals y3 plus v initial y, which in this case is v3 y times time plus 1/2 ay times time squared. V3 is 0, so that goes to 0. This is 0, and so what we're left with is 0 equals h3 plus 1/2 negative g times time squared. So we can move things around. 1/2 gt squared, it becomes positive on the other side, equals h3. And so if we multiply by 2, divide by g, and take the square root, you should get t equals the square root of 2h3 over g, and that would be your equation answer for question 3. Oh boy, now we're cruising. All right, so now maybe I'll move to a different color just again so that we don't get confused. So again, this was question 2 on the pre-lab. Now we're going to move on to question 3 on the pre-lab. And now we're asked to look at, again, 3 to 4, but in the x direction. Now this is a little easier because v3x is just going to be equal to our answer from part question 1. So right here, right, it's just going to be v2x. And then v4x is actually the same thing, v3x, because ax is 0. So x3 we define as 0. X4 is what we're trying to find. The time here is just going to be what we just found. So we could just call it the square root of 2h3 over g. Ax is 0 because things in projectile motion have 0 acceleration. And so if we wanted to solve for that x position, we can actually use this same kinematic equation, but apply it in the x direction. I'm just going to create a little more space over here for us. Oops. And so what we can do is we can say x4 equals x3 plus v3x times time plus 1/2 ax times time squared. Now again, since ax is 0, this is 0, this is 0. So our x4 is just v3 times time, or you could write it out either as v3x times the square root of 2h3 over g, or if you wanted to be even more accurate for your lab, you could actually plug in your v2 here. So the square root of 2g d sine theta. So that's, again, from the beginning part, and then multiply that by our time, which is the square root of 2h over g. And that is your big answer there. Oh boy, howdy. Now we're really cruising. Now, question 4 is another fun one. It's asking us to basically derive an equation for the range equation. So what we're going to be doing here is launching an object as shown at some elevation or height from, in this case, I draw it as if it's from the ground, but really it could be any height. You're just defining your 0 as the height that it is initially launched, and it has to land at that same height. So that's key for the range equation to work, is it assumes that whatever your y initial is, in this case, I'm going to define it as 0, your y final has to be that same height as well. So here we have some object launched at initial velocity v initial at some angle theta, and we're asked to derive an equation for its horizontal distance, the range. So again, the range, if I write it, would just be, again, the total distance that it travels here. So if we define x initial as 0, then x final is r. And I just realized I put y final in the wrong place, excuse me. So y final is here. There we go. All right. Now, let's think through these other variables. We know for anything moving through the air only under the influence of gravity, acceleration in the x is 0. and acceleration in y is just negative g, or negative 9.8 meters per second squared. Now, we don't know the time. We don't know the final velocity in the x or y. However, they are related to the initials. So the question is, what is the initial velocity in the x and y direction? Well, if we look up here, we can take our initial velocity and turn it into a little right triangle, where the opposite side is v initial y, the adjacent side is v initial x. And so using trig, just as we did on the previous ones, we can see that v initial x is just going to be v initial times the cosine of that angle, since it's the adjacent side of the triangle, and v initial y is going to be v initial times the sine of that angle theta. So now what we need to do is try to find the range equation. And to do this, we're actually going to have to use both x and y and put them together using the common variable of time. So for example, if I start with the x equation, second kinematic equation, that's x final equals x initial plus v initial x times time plus 1/2 ax times time squared. This is 0 and this is 0. So our range is just equal to v initial cosine theta times t. Problem is, we don't know what the time is. So to find the time, you actually have a couple different ways you can go about finding it. What I find to be the easiest is actually to look and determine that since it's starting and ending at the exact same height. Now there's, again, multiple ways to do this, but since it's starting and ending at the same height, due to symmetry, if my initial y velocity is v initial sine theta, then my final velocity is going to be equal in magnitude, but opposite in direction. So it's just going to be negative v initial sine theta. And so then I can actually use my first kinematic equation that says Vy final equals V initial y plus Ay times time. And so what we would have is negative V initial sine theta equals V initial sine theta minus G times time. And I can actually solve. So GT, adding that to the other side, then adding this over here is going to equal 2, since I have V sine theta plus v sine theta. So I have 2 v initial sine theta. And so my time is just going to be 2 v initial sine theta over g. And now I plug this time in to the other equation I have. So r equals v initial cosine theta multiplied by 2 v initial sine theta over g. And now I can rewrite this. So I have v initial and v initial. So that's going to be v initial squared. On bottom, I have g. And then what's left is 2 sine theta times cosine theta. So you could think, hey, look, I'm done. But this doesn't look like the equation in the lab. Well, that's because there's one fun other fact that you might not know or remember from trig class or pre-calc. But there's a trig identity that tells us that 2 times the sine of any angle multiplied by the cosine of that same angle is always equal to the sine of 2 times that angle. So don't get confused. That's not like 2 times the sine or something. That's different. So it's like sine of 30 times cosine of 30 times 2. This is equal to the sine of 60 degrees. So you double the angle and take the sine of that, and it works out a fun little trick from pre-calc. And so then if we take that and put it into our equation that we've been working on, our range equation, now we have v initial squared over g, and then multiplied by the sine of 2 times the angle that it's launched at. And that is our derivation. Pretty good, tricky question, but pretty good nonetheless. So that's it for pre-lab number 2. Again, make sure you have all of these in your pre-lab, and hopefully this will actually help you get more accurate results in the lab itself. Before I used to make these videos, a lot of people would have the wrong answers on the pre-lab, and therefore they would have huge percent errors in the actual final lab. So I hope that helps. Let me know if you have any questions, and yeah, I look forward to seeing your completed pre-labs.